In computer science, a selection algorithm is an algorithm for finding the kth smallest number in a list or array. Such a number is called the kth order statistic. This includes the cases of finding the minimum, maximum, and median elements. There are O(n) selection algorithms, and sublinear performance is possible for structured data. In the extreme, O(1) for an array of sorted data. Selection is a subproblem of more complex problems like the nearest neighbor and shortest path problems. Many selection algorithms are derived by generalizing a sorting algorithm, and conversely some sorting algorithms can be derived as repeated application of selection. The simplest case of a selection algorithm is finding the minimum element by iterating through the list, keeping track of the running minimum the minimum so far and can be seen as related to the selection sort. Conversely, the hardest case of a selection algorithm is finding the median, and this necessarily takes n/2 storage. In fact, a specialized median selection algorithm can be used to build a general selection algorithm, as in median of medians. The best-known selection algorithm is quickselect, which is related to quicksort. Like quicksort, it is optimal average performance, but poor worst-case performance, though it can be modified to give optimal worst-case performance as well. Selection by sorting the list or array then selecting the desired element, selection can be reduced to sorting. This method is inefficient for selecting a single element, but is efficient when many selections need to be made from an array, in which case only one initial, expensive sort is needed, followed by many cheap selection operations O(1) for an array, though selection is O(n) in a list, even if sorted, due to lack of random access. In general, sorting requires O(n) log n time, where n is the length of the list, although a lower bound is possible with non-comparative sorting algorithms like radix sort and counting sort. Rather than sorting the whole list or array, one can instead use partial sorting to select the k smallest or k largest elements. The kth smallest is then the largest of the partially sorted list This then takes O(1) to access in an array and O(k) to access in a list. This is more efficient than full sorting, but less efficient than simply selecting, and takes O(n plus k log k time, due to the sorting of the k elements. Partial sorting algorithms can often be derived from sorting algorithms. As with total sorting, partial sorting means that further selections can be done in O(1) time for an array and O(k) time for a list. Further, if the partial sorting also partitions the original data into sorted and unsorted, as with an in-place sort, the partial sort can be extended to a larger partial sort by only sorting the incremental portion, and if this is done, further selections above the kth element can also be done relatively cheaply. Unordered partial sorting if partial sorting is relaxed so that the k smallest elements are returned, but not in order, the factor of O(k log k) can be eliminated. An additional maximum selection time is required, but since this still yields asymptotic complexity of O(n). In fact, partition-based selection algorithms yield both the kth smallest element itself and the k smallest elements. This can be done in O(n) time average complexity of quickselect, and worst-case complexity of refined partition-based selection algorithms. Conversely, given a selection algorithm, one can easily get an unordered partial sort in O(n) time by iterating through the list and recording all elements less than the kth element. If this results in fewer than ka1 elements, any remaining elements equal the kth element. Care must be taken, due to the possibility of equality of elements, one must not include all elements less than or equal to the kth element, as elements greater than the kth element may also be equal to it. Thus unordered partial sorting and selection of the kth element are very similar problems. Not only do they have the same asymptotic complexity, O(n), but a solution to either one can be converted into a solution to the other by a straightforward algorithm. Partial selection sort equals. A simple example of selection by partial sorting is to use the partial selection sort. The obvious linear time algorithm to find the minimum iterating over the list and keeping track of the minimum element so far can be seen as a partial selection sort that selects the one smallest element. However, many other partial sorts also reduce to this algorithm for the case k equals 1, such as a partial heap sort. More generally, a partial selection sort yields a simple selection algorithm which takes kn time. This is asymptotically inefficient, but can be sufficiently efficient if k is small, and is easy to implement. Concretely, we simply find the minimum value and move it to the beginning, repeating on the remaining list until we have accumulated k elements, and then return the kth element. Here is partial selection sort-based algorithm. Function select, list, 1n, k, for I from 1 to k, min index equals I, min value equals list, I, for j from I plus 1 to n, if list, jn/2, and in place algorithms can select with only 1, additional storage. K storage is necessary as the following data illustrates: start with 1, 2, k, then continue with k plus 1, k plus 1, k plus 1, and finally finish with j copies of 0, where j is from 0 to ka1. In this case the kth smallest element is one of 1, 2, k, depending on the number of zeros, but this can only be determined at the end. One must store the initial k elements until near the end, since one cannot reduce the number of possibilities below the lowest k values until there are fewer than k elements left. Note that selecting the minimum by tracking the running minimum is a special case of this, with k equals 1. This space complexity is achieved by doing a progressive partial sort tracking a sorted list of the lowest k elements so far, such as by the partial insertion sort above. Note however that selection by partial sorting, while space-efficient, has superlinear time complexity, and that time-efficient partition-based selection algorithms require n space. This space complexity bound helps explain the close connection between selecting the kth element and selecting the lowest k elements, as it shows that selecting the kth element effectively requires selecting the lowest k elements as an intermediate step. Space complexity is particularly an issue when k is a fixed fraction of n, particularly for computing the median, where k equals n/2, and in online algorithms. The space complexity can be reduced at the cost of only obtaining an approximate answer, or correct answer with certain probability. These are discussed below. Online selection algorithm. Online selection may refer narrowly to computing the kth smallest element of a stream, in which case partial sorting algorithms space for the k smallest element so far, can be used, but partition-based algorithms cannot be. Alternatively, selection itself may be required to be online, that is, an element can only be selected from a sequential input at the instance of observation and each selection, respectively refusal, is irrevocable. The problem is to select, under these constraints, a specific element of the input sequence with largest probability. This problem can be tackled by the odds algorithm, which yields the optimal under an independence condition. It is also optimal itself as an algorithm with the number of computations being linear in the length of input. The simplest example is the secretary problem of choosing the maximum with high probability, in which case optimal strategy is to track the running maximum of the first any elements and reject them, and then select the first element that is higher than this maximum. Related problems. One may generalize the selection problem to apply to ranges within a list, yielding the problem of range queries. The question of range median queries has been analyzed. Language support. Very few languages have built-in support for general selection, although many provide facilities for finding the smallest or largest element of a list. A notable exception is C++, which provides a templated nth element method with a guarantee of expected linear time, and also partitions the data, requiring that the nth element be sorted into its correct place. Elements before the nth element are less than it, and elements after the nth element are greater than it. It is implied but not required that it is based on Hall's algorithm by its requirement of expected linear time and partitioning of data. C++ also provides an nth element template function, which solves the problem of selecting the smallest k element in linear time while reordering its input sequence. It can also be used to solve the problem of selecting the largest k elements in linear time by inverting the ordering, that is passing an std greater as the fourth argument. For Perl, the module sortKeyTop, available from CPAN, provides a set of functions to select the top n elements from a list using several orderings and custom key extraction procedures. Furthermore, the statistics case resampling module provides a function to calculate quantiles using quickselect. Python's standard library includes HEAP-Coon smallest and largest, returning sorted lists, the former in O, n plus k log n, time, the latter in O, and log k, time. Because language support for sorting is more ubiquitous, the simplistic approach of sorting followed by indexing is preferred in many environments despite its disadvantage in speed. Indeed, for lazy languages, this simplistic approach can even achieve the best complexity possible for the k-smallest greatest sorted if the sort is lazy enough. See also, ordinal optimization. References. External links, lecture notes for January 25, 1996, Selection and Order Statistics, ICS 161, Design and Analysis of Algorithms, David Epstein.